Question 3. Explaining triple bonding using molecular orbital diagrams by Jacob Price. Here is the molecular orbital diagram of dinitrogen. Nitrogen has 5 valence electrons, as can be seen either side of the MO diagram here. We have 2 electrons in both 2s orbitals and 3 in both 2p orbitals. The 2s orbitals here are fully filled, whilst the 2p are both half filled. This gives us 10 electrons in total. Down here, the 2 sigma G and 2 sigma U star must both be fully filled due to both 2s orbitals being fully filled. Whilst up here, first we fill both 1 pi U orbitals, and then, as we have 2 electrons left, we must fill the 3 sigma G orbital. So, even though there are 10 electrons, due to the 2 sigma U star orbital acting as an antibonding orbital, we can see from the bond order that it is free. And as it's free, we can know that this must be triple bonding. Carbon monoxide is a heteronuclear diatomic. Here you can see the molecular orbital diagram for it. The LOMO, which is the lowest molecular orbital, is 3 sigma, so this is filled first with the electrons from the 2s orbital of the oxygen atom. The order the molecular orbitals are filled is then 4 sigma, 1 pi, 4 sigma star. The 4 sigma molecular orbital gets its 2 electrons from the 2s orbital of the carbon and the 2p orbital of the oxygen. In total, 1 pi molecular orbital has 4 electrons. These are donated by the 2p orbital of carbon and the 2p orbital of oxygen. This leaves us with 2 electrons to go into the 5 sigma star molecular orbital, and these can be donated from the 2p or 2s orbitals of carbon or the 2p orbital of oxygen. As can be seen, if the LOMO is 3 sigma and is the lowest, then this would make 5 sigma star the highest, which is called the HOMO. The order that these go in is very similar to dinitrogen, in that it goes sigma, sigma, pi, sigma. Both have 1 antibonding orbital. However, in carbon monoxide, the antibonding orbital comes higher. Both have a bond order of 3, as can be seen from this calculation. Both have 8 electrons in the bonding orbitals and 2 electrons in the antibonding orbitals. This gives a bond order of 3, and this shows that, like dinitrogen, it should be a triple bond. Here can be seen the molecular orbital diagram of O22+. O22+ uses the same molecular orbitals as dinitrogen and has 10 electrons, which is the same number as dinitrogen, and has the same electron configuration of 1s2, 2s2, 2p3. However, In this molecular orbital diagram, the 3 sigma G molecular orbital is lower than it is in the dinitrogen molecular orbital diagram. Also, the 1 pi U molecular orbital is higher in the O2 2+ molecular orbital diagram than it is in the dinitrogen molecular orbital diagram. They have the same bond order of 3 and have the same number of electrons in the 2s and 2p orbitals as dinitrogen. Here is a comparison of oxygen and O2 2+. Here the electron configuration has decreased by 1 due to a loss of 1 electron from each oxygen. This means that both electrons are lost from the 1 pi G star molecular orbital of the O2 molecular orbital diagram to get the O2 2+ molecular orbital diagram. As we can see, the bond order of oxygen is 2, due to there being 8 electrons in the bonding orbitals and 4 electrons in the antibonding orbitals, whilst O2 2+ has a bond order of 3, due to 8 electrons being in the bonding orbitals and 2 electrons being in the antibonding orbitals. This is why oxygen has a double bond and O2 2+ has a triple bond. The bond order increases when removing electrons here because it was removed from an antibonding orbital